Hey guys, how's it going? Today I'm going to be going over solutions to round 672, and I can cover all the problems since I've ultimately solved all of them. You can see in the bottom right hand corner that it's kind of late right here because my schedule's been kind of crazy lately. So I'm going to upload this in a few hours from recording this, and the timing should work out fine. But you see that I'm staying up late to make this video, so you should definitely subscribe. Definitely subscribe. I'm gonna be committed. Yeah. Okay, anyway, that's not exactly a joke because you should subscribe, but it's not that serious. Anyway, whatever. So, I did participate in this round somewhat officially, but for half the time I was in school, and I didn't want to record school because, firstly, because it's slightly weird, and secondly, because it might accidentally give you a glimpse of facecam, which is definitely not what I want to happen. So, to minimize the chances of any like sneak peeks, because you know, facecam is going to come at 10,000 subscribers and no less. But yeah, I wanted to minimize the chances, so I just didn't record. But I can go over solutions now, and that's what I'm going to do. That was a long intro, Jesus. Okay, so this is A. I'm not going to go over the problem statements. I trust you can do that because don't have that much time. Yeah, okay. So initially, we noticed something important about this problem. Let's just take out this region. All right. So there's some quote, whatever. This is kind of like general ideas of parsing problem statements, and all of this is just part of the statement. But look at this number. This is a very specific number. The setters didn't do this by accident. This number means something, and we have to use this number and the very like oddness of this number to come up with a solution. Firstly, what are we actually doing to this array that we have? Let's take, for example, this 5, 3, 2, 1, 4. Then in any one move, we can swap two adjacent ones, and we ultimately want to sort the array. This is well known to be an algorithm called bubble sort, where you kind of take the biggest element and you kind of just bubble it to the end. But even if you don't know bubble sort, we can still use the ideas for this. Okay, first of all, n times m minus 1 over 2. That's the number we have. That's the number we have. This number specifically is the total number of pairs in an array. Because this number can have 4 different elements it can be matched with. This one can have 3 different elements. This one can have 2 different elements. And 1 and 0. And this is equivalent to saying n choose 2. You can work that out for yourself. And what that means is this number is exactly the number of pairs we have in any pairs of 2 elements we have in an array. So part of the reason why that's useful is because consider a pair that, consider like 2 indices, I'm going to say A and B, where A is before B, but at the same time, like the value, I'm going to say the value of A is greater than the value of B. Then, once we sort the array, these 2 elements are going to have to be swapped. And at some point, because we can only swap adjacent elements, these two values are going to be adjacent. Like, we don't care about what else happens. Eventually, these 2 values are going to be adjacent, and we're going to have to swap them. So this single pair of elements, where it's kind of unsorted, that is going to cost us a swap. Meanwhile, a well-behaved pair like 1 and 4 will not cost us a swap because it's already in sorted order. So no matter whatever we do to the other elements to get them in order, we're never going to have to swap these two. So the common terminology for elements like this, keep that, is called an inversion. An inversion is two positions that satisfy these properties. One is less than the other, but the one that's less has a value greater than the one after it. And that means that in this sort of like bubble sorting algorithm where we can only swap adjacent elements, each inversion is going to take us a swap. And every other element that's already sorted is basically done. Like, we don't care about that. So the maximum, like the number of swaps we're required to make ends up being exactly the number of inversions. Because every element that isn't an inversion is sort of well behaved, or every pair. And equal elements also don't form an inversion because by default they're sorted. So now, we already have a solution. The one possible solution would be to count the number of inversions and just see if it's less than or equal to this number. And once we do that, we'll know that if the inversions is less than or equal to this number, we can basically do whatever we want. I mean, we can just count the number of inversions. And there are many ways to do this. Most of them involve something like a Fenwick tree, and we can do that in O of n log n. But no, don't pause the video here. There's a better way. There's a much better way. Because we still haven't used the fact that this number, n times n minus 1 over 2 minus 1, is very weird. And again, to reiterate, this is the number of pairs in an array. So that fact becomes even more important now, because every inversion in the array has to be between a pair of elements. So we can kind of reverse this condition to say if we can't sort the array, then we need to have greater than this, m minus 1 over 2 minus 1. And specifically, we can also rewrite it as greater than or equal to n times m minus 1 over 2. And that means impossible. Otherwise, it's always possible because it's only the inversions that require swaps, and we have this many swaps that we can make. So we only need to check that the number of inversions is greater than or equal to this number. But we only have this many pairs in the array, and every inversion is going to form a pair. So we can't have more inversions than pairs. And therefore, it's never going to be greater than this. It's only going to be equal to this. And for it to be equal to this, every single pair in the array has to form an inversion. Like, every single element has to be out of place. For example, this element has the pair this array has the pair 1 and 4, which is already not an inversion, so it's going to be possible. Even if we have only this array with 2 equal elements, these don't form inversions, so it's going to be possible. Every element has to form an inversion. So if I put some element at position n, for example 7, every element after it has to be greater than 7. But now say I put some number here, say 5. Now every element here has to be less than 5. So if I put some element here, say 3, then every element here has to be less than 3, and so on, until we get to like the final value. And what it means is the array has to be strictly decreasing. You can't even have equal values because this pair wouldn't form an inversion. So that ends up being the final condition. It's only impossible if the array is strictly decreasing, otherwise it's always possible. This is a refreshingly simple solution to a problem A, but it can be very tricky to come up with. It could be easier to just go down the route of directly counting inversions, which is valid, but it's kind of more difficult to implement. So it might be easier to just keep thinking for a little bit more and see if there's anything else you can observe to simplify the solution. Because checking for a strictly decreasing array is very easy. You just compare each pair of elements, and if there's any pair that's where the left element is less than or equal to the right element, then it's not strictly decreasing. So that is a simplified solution. Okay. For B, again, I'm not reading statements. With a lot of bitwise stuff, we can kind of just do out casework. And an important representation of bitwise numbers is something like this. So we have the first bit times 2 to the something. Let's say, for example, we have 8 bits. So we have like some number that has 8 bits in binary. We can use any number of bits we want as long as the number of bits can fit the numbers up to 10 to the 9th. So that's fine. It doesn't necessarily have to be 8 bits, and in fact it's not going to be. Usually we'll work with 31 or 32 bits, or 63 or 64, which is just standard for data types. It doesn't really matter in this case. But actually, in terms of this example, we're going to work with 4-bit numbers, because otherwise I'm going to spend way too much time drawing out pointless things. So a bitwise number can be represented like this. The first bit times 2 to the something, plus the second bit times 2 to the something else, plus the third bit times 2 to the something else, plus the fourth bit times 2 to the something else. Specifically, this number is going to have value 8. If this is 1, you gain an additional 8, otherwise you just gain nothing. This is going to have value 4, this is going to have value 2, and this is going to have value 1. So this number has 0 times 8 plus 1 times 4 plus 0 times, this number up here, plus 0 times 2 plus 1 times 1. Summing all these up, we have 5. So this is how we can represent bitwise numbers. And this representation is cool because we want the bitwise AND to be greater than or equal to the bitwise XOR. That is the problem itself, right? So let's do what's called a truth table, where basically, if you've done some CS, you know, probably have nightmares about these things, and I've had them too, but they're very useful in this case. Let's say we have 2 variables. We have A and B, and we want to find the values of A and B and A XOR B, and we want to see how they differ and what happens. We only have 4 possible cases. Both are 1, A is 1, B is 0, A is 0, B is 1, or both are 0. So if this is true, this is 1, this is 0, this is 0, this is 0. And in these cases, the XOR is 0 if they're the same and 1 if they're different. So in this case, bitwise AND wins out, and in this case, bitwise XOR wins out. And in this case, nothing changes, which makes sense because with leading zeros, we don't want that to happen. Right, but notice something else about this bitwise representation. This number is either 0 or 1. All of these are either 0 or 1. Okay, I'm going to undo that. So now, what this means is that this segment can only be 0 or 4. This segment can only be 0 or 2. This segment can only be 0 or 1, and this segment can only be 0 or 8. Specifically, nothing more than those. And the sum of this segment is 1. The sum of these 2 segments is 3. The sum of these, the suffix of these 3 is 7. And continuing the pattern, 1 is less than 2, 3 is less than 4, and 7 is less than 8. And in general, this singular bit is going to have more weight than all of these bits combined. Which means that because there's no case where the bit is 1 in both of them, if this bit is 1 and the other bit is 0, for example, say we have 1xxx versus 0xxx and we want to compare them, this one is automatically going to win, no matter what these values are. Because this is 8 plus whatever the value of this xxx is. This can be different x's, of course. And this is 0 plus whatever the value of these xxx's are. But this can make a difference of at most 7. And this can, in the worst case, be 0, and in the worst case, this will be 7. But no matter what, it's still not going to compare to this 8. This 8 is too mighty. The biggest bit is too strong, and it just completely destroys all the other bits. So what that means is we only care about the highest bit in all of our input numbers. Because again, notice that there's no situation where they're both 1. Which means that as soon as we have a single bit set, for example, here, as soon as we have a single bit set in either of the numbers, we already know, we can find out what the outcome is going to be. Because when there's at least one bit set in the highest possible bit, then whatever this outcome is going to dominate all of the other outcomes. And the only time where they're 0, and therefore we ignore this bit and move on to the next one, is when both values are 0, which still supports the fact that we can only care about the highest or most significant bit in each number. And then once we do that, we just kind of like check everything. And specifically, the only time where bitwise AND wins is when both bits are set. Otherwise, XOR will win because the AND will be 0 and the XOR will be 1. And we only want the bitwise AND to win. So let's store some... Okay. Let's store some values. I'm going to make this very long, so I can scroll down as much as I want. Let's store some values. So again, we only care about the most significant bit in every number. Specifically, it would be this one and this one. So let's just keep like an array called count, or what it doesn't have to be called count, whatever you want, of the number of elements with this most significant bit, which I'll abbreviate as the MSB, because it is the abbreviation. Then this, like if we take any element with this as the most significant bit, we can pair it only with numbers that have that same most significant bit. So we're looking for the number of possible pairs we can take from a specific value of most significant bit, and this is basically just like if you remember from problem A, it's the number of pairs we have. Like it's that choose 2, which is equal to this formula, and so you can just sum this whole thing up and be done. For example, I equals 0 and 31, because that's enough to contain all of the bit, or 30, because 2 to the 30th is greater than 10 to the 9th, so you can represent all numbers using only the first 30 or 31 bits. So take the sum of this quantity and you're done. Okay. That's B. Alright, I'm going to do C1 and C2 separately because I solved them separately. C1 itself can be done with a very standard solution. In fact, it's dynamic programming. There are other solutions you can apply, but I'm going to describe this one because it came most natural to me. It doesn't extend that well into C2, but there is a possibility of solving C2 with a similar idea. So we store a 2D array DP. I did it differently. I stored it with 1D because I was like trying to rush, and it's easier when you have fewer dimensions, so it still works out the same way. where basically this is position in the array. And this is 0 if you've taken an even number of elements beforehand, or 1 if you've taken odd. In other words, it's the parity of the number of elements you've taken. And this is important because say you could have a sequence like the input, for example, 1, 2, 5, 4, 3, 6, 7. And you could have taken, for example, these 3 as a sequence, or you could have taken these 2 as a sequence. And one of these may be better than the other, but if you take this, then you're going to subtract the next element, and that's important to know what you have to do with the next element. But if you take this, you're going to add the next element. So it matters what parity you have, because that's important in like how you compute the answer. But anyway, once you have this DP, computing transitions is simple. Either you take an element or you don't, in which case it just pushes on to future states, and it's a very simple solution. Of course, once you take an element, the parity will flip, and you'll either gain or you either add or subtract that value depending on the previous parity. But yeah, you can work out the transitions. That's C1. It turns out to be very simple if you know dynamic programming. So C2, I'm stubborn. So I wanted to extend the dynamic programming solution into the harder version. And the harder version has updates where you can, for example, swap some values. So you have 1, 3, 2 initially, but then after a single query, you'll swap the first and second elements and you'll have 3, 1, and 2. So that's kind of annoying. As you can see, I'm going over my code here, and it was very not a nice extension, if you can see all of this. Yeah, so I don't recommend the solution. This is a purely algorithmic solution, basically not designed on any observations or anything about difference arrays. If you want to see a more elegant solution, you can check out I think Second Thread did that well. So he has a very smart solution unlike what I did here. Which I don't really understand, so I don't understand fully. So instead I'm going to go over a more algorithmic solution, which will kind of also apply into more situations. Like it's more general than specifically this problem. In fact, I think this is a very cool idea for other problems, but in this specific problem it turns out to be a ton of casework. So we're going to continue the DP solution, but the problem here is that we have updates. So let's say we have, I'm going to not adhere to the exact sample, but instead just do some stuff. So here, for C1, we would compute the DP value for the whole array, and that would be that. We would just compute the best value for assuming we have the whole array, and there are no updates, so everything's fine and dandy, and we're just done. But with C2, we can swap elements, and that's a problem because that changes the array, and so we may have to recompute the entire DP. Like, for example, we still have DP for the first 2 elements computed, but then, like, what happens here? We don't know. That's a problem. So first we can make the swapping operation. That's terrible. It's bad color. It's way too bright. Experimenting with new colors because I've been running out lately. So we can make the swapping operation into whatever we want. We can make it more algorithmic by saying, for example, say we swap A and B, then we basically set A to B and at the same time set B to A. You have to do these simultaneously, however you do that. You can't just like, you can't just naively set A to B and then B to A, because once you set A to B, then both of these values are going to be B, and so you don't know the original value of A anymore. So anyway, it just has to be simultaneous. Slight tangent. Hopefully that is something you would have to learn, because that's something that comes up a lot, like swapping elements in an array. But anyway, that's kind of irrelevant. What matters more is how we actually do this. And I'm going to move this over. What the hell did I just do? What matters more is how we do this at all. So we naively compute dp for the whole array. But what if we compute the dp for smaller ranges of the array and then combine them together? Because at the end of the day, the output of our dp is the sum of some sequence. So if we compute the dp for this, and then we also compute the dp for this, then we can combine our answers by just taking the best values of the sequence. We don't necessarily always want the best. For example, say like the best alternating sum we can get here is, I believe, 5. And correct me if I'm wrong. And the best alternating sum we can get here is 7, I guess. That seems right. But like here we have one element, and here we have also one element. So obviously we don't want 5 minus 7. Instead, if we're going to take some elements to subtract, what we actually want is the lowest value, because we know we're going to subtract it. So the lowest possible value is going to give us the best possible benefit when we subtract it. So in this case, the lowest possible value should be 3 minus 7, which is -4. So the best we can do here would actually turn out to be 9. That's right? We take 5 and then -3 and then +7. Yeah, that looks right. And okay, so if we compute the dp for some ranges and we want to combine them, then we have to not only compute the best for a given parity, that is an odd or even amount of elements, but we also have to compute the worst for a given parity. Then to compute all of these elements, to compute it for this big range, we combine the answers for the smaller ranges. And basically to do that, we just do some casework. For example, if we take an even number of elements here, and we take an even number of elements here, then this is going to affect best of 0 and also worst of 0, depending on what happens. And similarly for if you take odd and even here, even and odd, odd and even here, and also both odd. It just depends on what you do. And all of these are possible, so you have to consider all of these transitions. Even if we did this, how is computing ranges useful? Well, basically we just like stick a segment tree on it and let that do all the work. Because a segment tree is perfect for operations where we have to combine answers for specific ranges. So we can use the segment tree to combine answers for these types of information. And a swapping operation is now simply doing updates on a segment tree. And specifically, we're doing these updates. We're setting one value to a different value, and we're also setting this value to a different value. So it's just a basic type of update. And then sort of the base case for segment tree leaves, you just want to initialize with like the right form of infinity, or like either you take the element or you don't. If you do, then you have a parity of 1 because you have one element, and therefore the value is just the value you have. Otherwise it's 0, and therefore the value is, in terms of best, you would want it to be like -infinity or something, just some very, very small value. And for worst, you would want it to be infinity because you want to minimize that. And if you don't have any elements, obviously you can't have an optimal value, so it should be as small or as big as possible. But you would do out these transitions and basically kind of just bash it out. And I'm going to link my code in the description because, well, these are the transitions. Most of it's copy-pasted, so it actually isn't that bad to like think of, but it's still a lot. it's still very easy to mess up. I'm actually surprised I didn't mess it up. But that is the outcome. So again, here in these segment tree nodes, I have a specific structure for it, and then my segment tree will combine those structures via calling, or by just calling like op, which is the operation. You can define your segment tree however you want, but what I do here is I store the best and the worst, and then you just do a ton of transitions based on what you take from each left and each right side. You also have to consider the case where you totally ignore one of the sides, and the best answer for this purple is just the best answer for this range, or the best answer for this range. That's another case that should be taken into account, I suppose. Other than that, it's just the hardest part is writing the merge function, so that ends up being it. There are, again, many different solutions for this, but using a segment tree to optimize some sort of linear DP recurrence with updates, it's come up, I've seen it before. For example, in a USCO problem where you have to do that. So I think while it's definitely not the most elegant solution, it does have sort of its values in that it's more applicable to other situations. And that's why I chose to present this, because other people are going to choose to present the more elegant solution, and that's fine. But yeah, this makes it kind of different, I suppose. It's also annoying, but it's different. Anyway, that's C2. Yeah, again, if it's hard to do this, look at the code for sure. All the transitions are laid out here. Okay. 2 to go. So for D, what we're going to do is, well, this is definitely a combinatorics problem. We're asking for how many how many subsets of intervals of size k satisfy a specific property, so we have to count them. We're counting here. What are we counting? Well, we're counting intervals, obviously, subsets of intervals. So, what am I saying? There are a lot of different ways we can try to count things, but we have to be accurate. We have to not count things twice. For example, if we have this subset, we don't want to count it at both this point and both this point and that point, because both of these points are going to give us just the same subset. So we can't just kind of go through the points and then see how many intervals, how many segments collide there, and then just bash it out. What we can instead do though is fix some property of the subset that's specifically unique to that. And then because it's unique, we're never going to count it either before or earlier, because this specific property is unique to whatever we fix. That's one possible way to approach it, or we can use some sort of approach with inclusion and exclusion, but it's not applicable here. What we're going to do for this problem is just, well, the way to do it is or one way to do it. There are many ways to do it, but one way to do it is we can sort the segments by their starting points. Let me illustrate the first sample, for example. So we have 1, 7. We have 3, 8. We have 4, 5. No, 4, 5. 1, 3. No, wait, sorry. 6, 7. We have 1, 3. This isn't the most clear drawing, but it's kind of summarizing stuff. We have 5, 10. That goes far out. And 8, 9. So the first thing we can do is sort them by their left endpoint. That will prove to be useful later. And we can break ties just by the right endpoint. It doesn't really matter. So this is a 3 going to 8, right? Yeah. And then 4 to 5. And then 6 to 7. No, we have 5 to 10 first. Then 6 to 7. And 8 to 9. So now these segments are sorted by the left endpoint, and we can just make them increasing, whatever. And again, we break ties by this. So let's say, what do we want to fix? Well, we can fix the number, we can fix the size of the subset, and we can say that the size has to be greater than or equal to k. And that's a possible idea, but like you can think about it for a while, and maybe there is some way to do it, but it seems hard. You have to apply something like inclusion-exclusion, and there's a lot of things to take care of. You have the intervals and stuff. So we should probably try something else. What if we instead fix, say, one of the endpoints? Let's say that this, let's say for example, this segment has the rightmost left endpoint of the set. And what that means is because we sort them by left endpoint, this, in terms of the array of segments, this is going to be the last element. All other segments have to be here. And this satisfies the uniqueness property that we want for not overcounting. Because obviously, if everything is on this side of the array, we don't take anything from here, and we mandate that we take this element, which means that we couldn't have counted any of these sets when we count anything before because we wouldn't have had the opportunity to take this element. So we won't count any of these sets before, and because we're going to have some unique element in any of these sets that we aren't going to have here, we aren't going to count any of these specific sets later. So we won't overcount using this. And that basically means that if we can efficiently compute the ways once we fix one of the endpoints, then we're just done. Okay, so we want everything to intersect with this segment. And we know that everything before this has a left endpoint before or the same as this. Which means that if some segment before this is going to intersect this segment per se, is going to intersect this segment, it's going to intersect it at the left, because the left endpoint is going to be like either to the left or the same as whatever this segment's left endpoint is. And all the other ones are going to be on the right, but we're ignoring those. So what that means is instead of counting the number of segments that just intersect this and worrying about where they intersect and if some of them end, for example, we can have something like this where this is an annoying case because we don't have any overlaps here. And that's different from this, for example, but in the same case, we have two segments that intersect with this. We only care about if they intersect specifically the left endpoint of this segment. Because again, any segment that comes before this in the array will be guaranteed to intersect the left endpoint. So we only have to count those. And the way we do that is simple. We can basically do a sweep line, and what that does is we drag a line here. And then we just kind of go through the segments. And we say, okay, now this segment has a left endpoint before, so we say that that segment is now part of, this segment, this orange one, is now part of, it's included. And then once we get here, we count both this red one and this other red one. And so both of these segments are now included. Then once we get here, this segment ends, so we now exclude it, so we only have two segments. Then once we get here, this segment ends, but this segment starts, so we end up with a net change of 0 segments. Here we get another one, here we both lose and gain one, here we get another one, here we lose one, here we lose 2, I don't remember the exact coordinates. But the point is, at every point, we can maintain exactly how many segments intersect this point by we go through and we add 1 for every beginning, and then once we reach its end, we subtract 1. So once our sweep line reaches this exact point, we'll know exactly how many segments are going to intersect with this. And I think in terms of intersections, this doesn't count. Like this intersection where their endpoints are the same doesn't count. They have to have some like actual amount of area. I think that's how it works. So be careful with that in the sweep line. But actually, I'm not sure. Maybe not. Actually, it does have an area. It just has infinitesimal area. I think actually. Yeah, that is right. They have to have like a non-infinitesimal amount of area. So it should be, for example, 1. They can't just have the same endpoints. They have to actually overlap each other. Anyway, that's just something else to consider in the sweep line. So a nice way to do the sweep line is simply iterate over all the left endpoints in like the sorted order, and then put all the right endpoints separately into an array. For example, we have 3, I'm not going to use commas, 3, 5, 7, 7, and of course, and we'll sort them so that they're also like sorted. And we don't really care about the left endpoints because we know that the left endpoint is less than or equal to the right endpoint. So if we get here, and this means that this segment is ended, we can already guarantee that it's already like begun because the left endpoint is before this. So regardless of whatever the left endpoint of this is, we know that once we get for like the target left endpoint, this blue square here that I've drawn a bunch of arrows around, once we get here, we can automatically subtract 1 because we're already going to have hit the beginning of the segment and we'll have already added +1 at some previous time in the past. So we now subtract this because the segment ends. And then for each left endpoint, which I'm going to draw another arrow to, we want to know the number of ways we can pick the other segments to make a subset that includes this. And with a bit of combinatorics, this is basically, say you have R amount of segments that intersect this point. Just keep drawing arrows to it. Well, we also know that this segment intersects this point. So it's going to be R minus 1 because we by default take this segment, so we subtract that from the count. And then we automatically again take this segment. So of the remaining k, we've already taken 1. So here we have to take k minus 1 out of these. So it ends up being R minus 1, choose k minus 1. Where if this is less than this, then the answer would be 0 because we can't choose k elements. So yeah, if you're unfamiliar with sweep line, I suppose you can also search that up because there's some nice resources online for that. Some like videos or whatever, better than, I mean, like animations and or just good blogs. So you can check that out if you don't understand my description of it. And once you do the sweep line, then you're just interested in the sum of this quantity over all of the possible endpoints. And you sum that up and print it. That's basically the solution. Okay, E is a fun one. I'm going to try and not spend an hour on this because it's a very elaborate problem in a sense. And I will admit I did not get this problem myself. Part of the solution is inspired by some of the editorial. And also talking to some friends about how to solve it because they're smarter than me. So yeah, anyway, let's just start with the problem. We're going to make a few changes to the statement to make it easier to solve. First of all, counting the number of pairs of zeros with a 1 between them is kind of awkward. So what we want to do instead is we want to make this into a more like easy to count form. And one way to do this is called counting the complement. Basically, if you've seen A and B, you know we have exactly n times n minus 1 over 2 pairs in an array. And we're interested in the number of pairs of zeros where there's at least one 1 between them. So we can instead count the number of pairs of elements where there isn't a 1 between them, or they aren't zeros. So for example, any pairs of the form of this are automatically disqualified because they aren't both zeros. And also any pair of zeros where there isn't a 1 between them is also invalid. So it turns out to be easier to count the number of invalid pairs and then subtract that from the total number of pairs, which gives us the number of pairs we actually want. And that's easier than just directly computing the number of pairs we want. Okay, so counting the number of ways 1 is paired with 0 is simple. It's just the number of 1s times the number of 1. Actually, it's both of these, because it's the number of 1s times the number of 0s. Because each 1 will be paired with every single other 0, regardless of whether it's on its left or on its right, which means both of these cases are kind of analogous. And yeah, every 1 will be paired with all of the 0s at some point. So it's the number of 1s times the number of 0s to pair it with, and therefore we get that quantity. So that part is simple. In terms of 1-1 pairs, it's again just this quantity, except where n is the number of 1s, because we're looking for the number of pairs between 1s. So it's the count of 1s times the count of 1s minus 1 over 2, just the number of pairs of 1s we can have. This is the hard part. This is why it's a div2e and not something simpler, because we have to do even more we have to make even more changes to the problem to figure out how to do this. So without further ado, let's make these changes. How do we compute the number of pairs of zeros where there's not a 1 between them? Let's write out this sequence from the second sample. We have 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 0. Okay. Now, this 0 has no other pairs of zeros it can be paired with. It has no other zeros it can be paired with because it's blocked off by 1s on both sides. And the same goes for this one. Everything on the other side of it is a 1. But these 4 zeros can be paired with each other without there being any 1 in between them. Specifically, we compare this one with any of these 3, then we compare this one with any of these remaining 2, then we compare this one with this remaining 1. And any 2 zeros in this subgroup can be paired together. And in fact, any zeros in any of these subgroups can be also paired together, but we just can't pair any of these together because there's only 1 in each. But there are 4 in these, and so the answer for this subgroup is the number of pairs, which is once again n times n minus 1 over 2, or I'll call it like k or something. K times k minus 1 over 2, where this k is just the size of the subgroup, or the number of consecutive zeros. So we want to minimize the sum of this, because all of these are like bad pairs, and we want to maximize the number of good pairs, so we want to minimize the thing we subtract. So we want to minimize the number of bad pairs. Now, zeros and 1s are also an awkward representation because you have to kind of consider their positions in the array. So we're going to make another alteration to this statement. I'm going to erase these annotations, and we're going to kind of let each one split the array into a bunch of different groups. Specifically, we're going to keep track of the sizes of all of the groups of zeros. And this kind of makes sense because the answer is just the sum of the number of pairs in each of these groups individually. So we might as well just keep track of these sizes, since we don't really care about where the 1s are, we just care about the zeros. So we would change this array to something like this. We have 4 zeros here at the beginning. In between this group, we have 0 zeros. Same goes here, we have 0 zeros, and same here, we have 0 zeros. And here, between these two 1s, we have 1 0. Here we have 0, and here we have 1. This is perfectly representative of our array. And we can also like kind of restore the original array because we know that it's just this many zeros and then like a 1 stuck in between all of these. And even if we have some sequence where there are 1s at the end, then this is still just, this is 1, this is 0, and this is 0. And we'll also consider having an extra 1 on the end because this 1 should split, like it should split this region. So we'll have an extra 1 on the end here. And that forms a group of 0. Because we could theoretically move this 1 all the way over here to the right of all of the, or we can move this 0 all the way over here to this group. We wouldn't want to, but that's a possibility. So we should consider endpoints too. And in terms of the implementation of finding these groups, what you can do is you can simulate it by sticking a 1 on both of these ends, like a virtual 1. And then you can do kind of a 2 pointers approach where you set one pointer to here. And then once you get to another 1, you know that you're at the end of this group. So the number of 1s here is just this distance. And then once you do that, you can move this pointer over to here, since this is the new left endpoint of the new group of zeros. And then you just keep on going. Here you know that it's this distance, which is 0. And then you'll move the pointer here, and then here, and then here. And then once you get here, you ignore this 0, then you get to this 1, and you know that this is a group of zeros, so this is of size 1, and etc. And sticking the 1s at the beginning and the end makes this implementation totally work, because it'll also capture the groups of the endpoints. And even if there's nothing on the end, it'll make an extra group of size 0, which is exactly what we wanted. So that's perfect in terms of implementation. So for the remainder of the problem, we're just going to consider this reduced sequence. Sorry, I think my speech is deteriorating as it gets later. But yeah, so I'll try to make this a bit quicker, I guess. So now we're just interested in, let's say G is the number of groups. So for example, in this, G equals 7. Then we're just interested in minimizing the sum of, like, Ki is the size of each group. The sum of, like, the number of pairs of zeros we can make. Now we can do operations. What we can do is swap 2 elements. What does swapping 2 elements do to these groups? Let's just draw out some zeros and 1s and see what happens. First of all, there's no point in swapping 2 zeros. And similarly, there's no point in swapping 2 1s because it's just a waste of a move. So we're going to assume every swap we do switches a 0 and a 1. Right now we have 3 elements in this group and 2 elements in this group. And say we swap these. So now we're going to have these 2 elements from this group. We're going to have a new 1 over here, a new 1 over here, and a new 0 over here. So we end up with 3 elements in this group now. Specifically, this 0 gets moved from the left group to the right group. So it's equivalent to saying a single operation is subtracting 1 from one number and adding 1 to an adjacent number. For example, subtracting 1 here and adding 1 to either this or this. As is obvious, we can't subtract 1 from something where we don't have any zeros in the first place. So we can't do that. Which again fits the description of the problem. So all this is working out, kind of. So now we have k operations we can do. Each operation entails, essentially it moves a value from here to here. Because it subtracts 1 from here and kind of moves that 1 over, and moves that 0 over to here, which also makes sense if you think about it in the context of the original problem. We're moving a 0 from one side to the other. So the operation is moving a single value across, and we want to minimize the sum using at most k operations. Now the go-to here is a dynamic programming solution because all the numbers are small. This is 80. So the number of moves is at most, as given in the problem statement, the number of moves is at most 80 times 80 minus 1 over 2, which is 3160. So that's a small number in itself. We only have O of n possible groups, so that is also n is 80. So both of these are small numbers. If we multiply them, the number will also be small. It'll be like 250, 60, whatever thousand. Yeah, 252,800. That's a small number. Unfortunately, though, doing some sort of DP on generally the normal standard DP solution to things with arrays is you solve for some prefix, and then you use the solution for this prefix to extend it to adding this element into the prefix. However, just storing the number of moves made and the prefix we're at isn't enough for dynamic programming. We need more information because we kind of, like maybe we made some, like say we've computed this prefix, right? But maybe we made some swaps that move some elements out of this prefix. We need to store that. Maybe we also did some things where, like, say we said we wanted to increase this to 2, which means that we actually need to move both of these 1s over to here somehow. We need to keep track of that as well. And, well, both of these are important. But also both of these are kind of the same. Because if we think about it like this, say we change this to 1, and then we just move the rest of these 3 elements over. If we move it within this prefix, that's fine. We can even like spread them out within this prefix. Whatever we did here, that's fine. But if we maintain that both of these are 0, then we have to move all these elements out of this prefix. So it's kind of like saying there are 3 elements that we have to cross this barrier with. And yeah, basically there are 3 elements that we have to cross this barrier with. So as long as we keep holding on to these 3 elements, we have to move all of these 3 elements to the next position and the next position and the next position. But storing only the fact that we have to move 3 elements to the right is enough. We don't care about the position of where these elements started, because we can abstract out the position by just saying every time we still have 3 elements, it takes us 3 more moves. So we're kind of doing out the moves as we move along in computing the array with prefixes, instead of trying to worry about sums of positions and stuff. That way we only care about the number, and we use that number every single time to count the moves between the gaps. So that works for moving things to the left. What about to the right? Or moving things to the left, sorry. What about to the left? We want to move both of these 1s somehow over here. If we consider only the prefix, it's kind of like saying, it's kind of like being in debt, kind of, where we need to pull 2 of these 1s from the future and then bring them back into this prefix. So we say that we have two 1s that have to cross this prefix going this way. And it's basically saying, like, it's the same exact thing. Either we have, for example, we have 3 that want to go this prefix going to the right, or we have 2 going to the left. And we can summarize this in one number by just saying all of these are positive and all of things going to the right are negative. So this would be, this state would have positive 3 and this state would have negative 2. That's enough information, because that will uniquely give us the number of moves we need to make, we can store the sums in the answer, and we immediately know, like, we don't care about what's going on in this prefix anymore. All we need to know is that eventually we need to bring 2 1s over onto this prefix. And however we do that, we can figure that out in the future. Or we're carrying over 3 of these 1s from the prefix and we're bringing them into the future. But again, we don't care about anything else that happened in that prefix, only the number of 1s that are crossing this red barrier. And that's all the information that the prefix will give us. So storing only that in the DP is enough. So yeah, then once we do that, transitions are simply we fix whatever we want this element to be. It can be any number in the range 0 to n, inclusive on both. And then say we want this number to be 3. Then if we have some det of 3 coming from here, then that means we can bring these 3s onto this. So we have to, running out of colors again, so we have to increase this element by 3, and we have a det of 3 here. So we might as well just use these 3 1s to increase this element. So now our det decreases by 3. So if we change our AI to some new value x, and therefore the difference is x minus AI, then the difference in the delta is the negative of this, or AI minus x. So in this case, the, not delta, what is it? Like the amount we're carrying, the det, will decrease by the change. It actually doesn't matter which signs you use, because all you care about is if they're 0 or not at the end. Because in the final array, you have to have a det of 0. You have no more future to pull elements from, so you have to have resolved all of the movements, kind of. If you have any det other than 0, then you have more than the number, you have more or less than the number of zeros you had in the original array, which is obviously not possible, so you can't do that. You have to have resolved all your det, both positively and negatively. Yeah, so that's the transition. And of course, if you decide you want to decrease this number, so you want to say make it like -1, for example, or just assume this number was bigger than 0 and you would want to decrease it by 1, then basically so I kind of mixed it up, didn't I? I think I did mix it up. What you want to do is, if you want to increase this to 1, then you'll have to pull some stuff out of the future to be able to increase this to 1, I guess. So it ends up being like your det increases by 1, I think. Is that how it works? That shouldn't be how it works. If you have 1 here, so if you want to increase this by 1, then you have to pull some 1s out of the future, out of the past. And if you want to decrease this by 1, so you want to make this -1, then this will increase your debt. Or it'll increase the number of ones you have to get rid of. Because now you have an extra one that you're kind of moving along over here. It all depends on what you define debt to be. Either it's the number of ones that you're carrying over or the number of ones that you need to move back. Like e.g. positive or negative. So yeah, it's not that important. Basically, I can leave you to work out the details for yourself if you want, and you probably should, because working out the details will help you understand it more. Basically, the transition is you can make this element anything from 0 to n, and then you figure out what that does to your debt. So again, for example, if I decrease this to -1, then that means I'm getting rid of a 1 here. So I'm going to have to push this 1 out to the future somewhere. And if I'm adding this to 1, then I'm getting rid of one of the ones that I'm carrying over from the past, which means that I have one fewer 1 now that has to go like past this prefix, which again could be negative. It depends on what you have. But that's the transition. You change this to anything, and then the DP value is going to store like the minimum sum that you want to minimize. So you would just add this value for whatever you want to make it. Of course, you have to try making it everything. So then the final like DP thing is DP on position the kind of debt and the number of moves you've already made. It should be clear how to get the additional number of moves from the debt. Basically, if you have to carry 3 things over the barrier, it takes 3 moves each time for each barrier. And if you have to carry 2 things this way, it's still going to take 2 moves. So it's basically like the absolute value of debt. That's how many more moves you have to spend each time you move something. And then this will store the minimum sum. The minimum sum of that. Assuming ki is like the new thing you change for each element in this sequence. That basically does it. One final note is that sometimes you can't store negative debt, but you can also notice that in any reasonable solution, the debt will be in the range of -n to n, because otherwise, like, you'd have more than n zeros, and that doesn't make any sense. So what you can do is, instead of accessing an array at negative indices, you can access the array at debt plus n. And that way everything will be at least 0. And the reason this works is because the original debt is in the range of -n to n. So debt plus n will be in the range of 0 to 2n, because you just add n to both endpoints of the range. And therefore this is usable with an array. So because there are n possible values you can change an element to, this is complexity-wise technically O of n to the 5th. And 80 to the 5th is not the best value. It's kind of on the large side, as 3 times 10 to, or 3.2 or 3.3 whatever, times 10 to the 9th. It's not the greatest, but at the same time, these are not very computationally expensive operations, and at the same time, at least half of these states aren't going to be visited. For example, you can't be at position 1 and already have used like 1,000 moves, because n is never going to be that big. Many of the states aren't ever going to be visited, so you can engineer it so if you haven't ever visited a state, just don't bother with changing the position because it's never going to get you anywhere. That's an optimization you can make, and that should be enough to get your runtime below what you need to be. My solution used a lot of stuff. It had 1201 out of 2 seconds, 1201 milliseconds out of 2 seconds, or 2000 milliseconds, and 350 kilobytes out of 512 megabytes, so it's kind of close. But it's not terrible. I have 350,000 kilobytes, I guess. Yeah, once you do that, probably would have been better to make it asymptotically slightly better by maybe reducing the constraints, like 75 to the 5th or 70 to the 5th would be nicer at least, and probably more friendly for other people, but this ends up working nonetheless. Yeah, and so my code goes over how to do these transitions. There's a lot. It's kind of messy, but mostly it's just figuring out what the previous state is and then using that to figure out what the new state will be, and then you just update the answer. Then the final answer once you have the DP value is, well, you can kind of take a suffix maximum, or no, sorry, that's like wrong in every sense of the word, isn't it? Yeah, if you write out like the final state for a fixed number of moves, say you were using like X moves, then the final state is DP of N, because you're at position N at that point, and then the det has to be 0, and then it's X. So you can use a prefix maximum of dpn, which is like the maximum over dp of n and 0, and the values 0 to x. And then, or sorry, it should be the minimum, because you're subtracting that, and you want to maximize the number of good pairs you have. And this is the number of bad pairs. So the final answer is doing the math out from previously. It's n times n minus 1 over 2 minus the count of zeros times the count of ones. Again, this is all just the same math from before. Minus the count of ones times the count of ones minus 1 over 2, and then minus this minimum. And all of these are the pairs that aren't of the form that we want to count, like 2 zeros with some number of shields, like at least one shield in between them. So all of these are the bad pairs. So we want to minimize this quantity, and that's why we minimize the DP. And the rest of these are just fixed based on the input, so that's simple. And yeah, that's basically it. Just take the prefix minimum over all the DP values once you're done, and you can print the answer. Okay, I think that's good. Kind of a bit, maybe probably sloppy, but it's fine, I suppose. So I'll upload this tomorrow in the morning sometime, and we'll work that out. Or in the morning for me, probably not for many of my viewers, but yeah. I'll find some time, it'll be good. Probably soon. Yeah, that's about it. I have nothing more to say. I hope you enjoyed. Wasn't the most enjoyable thing, but at least hope stuff made sense. Okay, that is enough. Goodbye.